Hey there, everyone. Just looking through some of the posts online in discussion board, and it seemed as though the idea of span was possibly a bit nebulous. So I thought I would just spell it out a little bit and then use an example to hopefully give it a concrete meaning. So jumping into it, the span of n vectors. So I've written here the span of v1. Oopsie, let me start again. The span of v1, v2, all the way up to vn, so n vectors. The span of those is simply the linear combination of those vectors. Okay, so still nebulous, so we'll move to the next slide. So we might want to define what a linear combination is. So for any values a1, a2 up to an, and we write this as the elements are real, which just means any value. So it could be -1, it could be +2, it could be pi, any of those numbers. A linear combination of our n vectors is simply a constant times our first vector plus a constant times our second vector, and we do all that all the way to our last vector, where we do a constant times our last vector. So that's the definition of what a linear combination is. Alright. So to make this a bit more believable and understandable, I've come up with an example here. So here I've written the span of v1, where v1 is the vector 1, 0, and v2, where v2 is the vector of 0, 1. We're going to discuss what the span of v1 and v2 is. So I've drawn a little picture down here, and this is often referred to as R2. So it's simply the two-dimensional plane. So we can see the vector 1 is simply going from the origin in the middle out to the coordinate 1, 0, and v2 is going to the coordinate 0, 1. So I've written this slightly different to up there, and I've written that slightly different to up there, but they both mean the same things. So I guess if I was in a classroom, I'd ask anyone got any ideas what the span of this is. But it's just me in front of a tablet, so I'm just going to come out and say it. So it turns out the span of our two vectors here is the entire r² plane, or the 2D plane. And on the next slide, we'll start to work towards why that's the case. So the span of v1 and v2 is any vector satisfying a1 times v1 plus a2 times v2, where a1 and a2 are real. Okay, so what does this mean? So if we took a1 to be 2 and a2 to be 0, our end result of this equation would simply be 2 times 1, 0 plus 0, 1, 0, which would be simply 2, 0. So the reason I use this example is I'm hoping this can start to show you that we can get anywhere in R2 by using a linear combination of v1 and v2. Okay, so once again I've just got another vector here. So this is an element of R2, poorly drawn. I'm going to try to show you that it's in the span of our vectors v1 and v2. So if we consider our two-dimensional plane, and we have our v1 as before and our v2 as before, how can we get to the coordinate 3, -1? So we could use a linear combination of our v1 and v2. where we'd find our linear combination as this. So if we took specific numbers for A1 and A2, my money's on that we could get to 3, -1. So let's go to the next slide. So I'm here to try to show you that 3, -1 can be gotten to using a linear combination of our V1 and V2. So if we were to take A1 equals 3 and A2 equals -1, then our linear combination becomes 3V1 plus -1 V2, and we can go ahead and plug in what our V1 and V2 are. So we've got 3, 1, 0, take 0, 1, which means we've got 3, 0, take 0, 1, which simply equals 3, -1 as required. So we can see that in the previous slide where we had our xy coordinates and we had our V1 and our V2. If we wanted to get to the coordinate 3, -1, we need to take 3 lots of our V1. So we go 1, 2, 3. Oh, I drew that poorly, so that's where our 3 is. And then, so we've got 3 lots of V1, and we're going to take -1 lots of V2. So it just turns the vector around, and that is -V2. So if we add our 3 lots of V1 with our -V2, we get to our point there. So we can start to see how the span of two vectors is simply using the combination of the vectors and expanding them or shrinking them as we need to get to any place. So I hope that I've convinced you that we can use our V1 and V2 for our specific span to get anywhere in our R2. So all these points that I'm making here, they're just different combinations of V1 and V2. So we can even start to go out all the way out here, and it goes off to infinity. So I think this is the basic idea of span. So here we've got elements of the two-dimensional plane, but obviously it generalizes to larger dimensions and things like that. But you can see if you add more vectors, as long as they're linearly independent, you've got more places that you can go within your span. So our span here was a plane in 2 dimensions. I might put up a PDF soon about all the different possibilities for spans. Alright, I hope this has helped.